In order to get my revenge against Rakis the Destroyer, I have to make a new weapon.
Alex's weapon of choice is now a solid foam cylinder, rotating at about an axis perpendicular to its length. Let's see how good of a weapon it makes.
We are now going to calculate the moment of inertia to determine how much of a punch this weapon of mass destruction is going to pack on Rakis the Destroyer. In order to calculate moment of inertia, we have to know the radius, length, and the mass of the object. The first thing we're going to calculate is the length. The length of the weapon is approximately 6 inches long, which is 15.24 centimeters. Next, we are going to calculate the radius. The radius is approximately half an inch long, which means that in centimeters, it is 1.2 centimeters long.
To measure the mass of the weapon, we have created a jerry-rigged scale due to the lack of resources. What we have here is a camera battery serving as the fulcrum with a ruler serving as the seesaw. And so what we did is we placed a cup at one end and our object on the other, and then we filled the cup with water until it was equal in weight. And so now we found that exactly 10 milliliters of water, as measured by a medicine cup, sets the thing in equilibrium. 1 milliliter of water is 1 gram, so our object weighs 10 grams.
Because our object is not a point mass, we have to consider the fact that the mass of the object is evenly distributed throughout the entire thing. Therefore, we have to divide it up into cross-sections. The cross-section of our cylinder, with its axis going through the center, perpendicular to its length, is going to be a disk with a width of dx. For the purpose of calculus, dx is infinitesimally small, since this procedure must be done an infinite amount of times. Due to the fact that the mass of the cylinder is evenly distributed for each section of width dx, there's an infinitesimally small mass that can be calculated, dm. This section of mass, dm, can be calculated by using m divided by l times dx, since m over l gives you the mass per meter of length and dx specifies how many meters of length.
To continue this derivation, we have to find the moment of inertia of a disk rotating about the given axis. Since this disk does not lie on this axis, we have to use a familiar equation that follows as such. The moment of inertia with regard to an axis parallel to the axis that passes through the center of mass can be found using I equals moment of inertia through the center plus mx squared, where x is the distance between axes. In this case, I sub c is the axis through the disk and I is the axis through the cylinder. All terms have a d in front of them because this operation will be repeated an infinite number of times to accommodate all disk subsections. Now we have to find the moment of inertia of a subsection, which is a disk. The moment of inertia for this specific shape is I equals 1/4 times mr squared, which we will plug in for I sub c.
When we plug in what we know so far, we get this: di equals 1/4 dmr squared plus dmx squared. Now the moment of inertia equation could be found by simply integrating this equation, which will leave us with I instead of di. To integrate it, we will integrate both parts of the equation separately. Also, it is important to note that you could substitute dm for m over l dx, since this is the equation we demonstrated before. So with that substitution in place, all integration will be with respect to x, which runs lengthwise. For the integration, the lower limit will be negative L over 2, and the upper limit will be L over 2. These limits come from the fact that the cylinder extends L over 2 in both directions from the central axis.
Now we're going to go step by step in the integration that we showed you before. So now at the very top we have our integration equation. So now because this is in respect to x, we have to add an x when we integrate it. And we're going to evaluate that the limits L over 2 and negative L over 2. When we evaluate those limits, we get this right here, which simplifies to simply L, and because we have an L on the bottom, those cross out, leaving us with 1/4 mr squared.
So in the next part of the equation, we have basic integration of m over L x squared dx, and we have the limits of L2 and negative L2. So when we take the first integral, we take m over L times x cubed over 3 with the limits L over 2 and negative L over 2. So when we plug in the limits, we come down and we have m over L times L to the third over 8 plus L to the third over 8 over 3. And when you add them up, you should get 2L to the third over 24. The L's cancel out, leaving 1 over 12 ml squared. And in the final step, once we come down to the last two integrations, we just add them together, and the moment of inertia of a solid cylinder is equivalent to 1/4 mr squared plus 1/12 ml squared.
As derived before, this is the moment of inertia, and we're going to be plugging these values in. Alright, so we plugged in all the values, and this is what we get. As a final answer, we get 1.98 times 10 to the negative 5th kilograms times meters squared.
Rakesh the Destroyer! I have come to get my revenge! I've created a new weapon, and it has a moment of inertia of 1.98 10 to the negative 5th. I think that's pretty good.
I have a new weapon too. Oh god. I destroyed him.